Okay, in this video we're going to look at some wave properties. We're going to look at how we can represent longitudinal waves a bit nicer as well. Because longitudinal waves, as you saw in the last video, we can only really represent by showing the particles in their compressions and rarefactions. But there's a nicer way of representing it, and you just have to make sure you don't get confused between the two kinds of waves when we do this. So obviously a longitudinal wave is where you've got particles that are moving backwards and forwards just like that. But as we just said, it's very, very difficult to represent that oscillation visually. So what we can do is we can represent it on a graph. Now the problem is that this is going to look very much like a transverse wave with oscillations going backwards and forwards, but when you realise what's going on here, it won't be so bad. So on the y-axis here we've got displacement, so that's how far it's been displaced from its equilibrium point. We'll deal with those words later. And this will be within an amount of time that it occurs. So what we've got here is we've got a situation where we can represent the oscillation of a particle going like this. Now all that means is that we are saying that a particle is moving from its equilibrium position, i.e. this middle position right here. That's the equilibrium position, we'll call that position 1, to a position where it's at a maximum displacement. So we've got a maximum displacement right here, we'll call that position 2. On the graph, this is represented by this position here, position 2. Obviously, it's an oscillation, so the particles are moving backwards and forwards, backwards and forwards. So the point is that it then passes back past its equilibrium position. We'll call that position 3. And moves on to, again, a maximum displacement, but this time on the other side. We'll call that position 4. And so what we have here is a situation where eventually it's going to return back to the equilibrium position. And that's this movement that occurs right here, and we'll call that position 5. So we've represented here, effectively, the motion of this particle going from left to right and back to the equilibrium position. Left, back to the equilibrium position, to right, back to the equilibrium position. So we've got a particle doing a full movement of okay? So it's just a really, really nice way of representing not just a longitudinal wave, because we can, but we can also represent transverse waves in exactly the same way. So, but the difference is it's much easier because that displacement is physically represented by the shape of the wave that you see here. So instead of the positionings of the waves being there, it's just smeared a bit, just rub that out. Instead of the positionings of the particle moving backwards and forwards, now these represent positionings of a particle moving up and down. So we've got a particle moving up, starting from an equilibrium position at position 1, then it goes up to a displacement at position number 2, it comes back down to its equilibrium position at position number 3, position number 4 it continues down to, and then comes back up to the equilibrium position for number 5. So in this case, this is a transverse wave doing that. There's your particle right here, moving up from position 1 to the maximum displacement, back down to its equilibrium position at number 3, onwards to the other side of the oscillation at position 4, and then back to position 5 for the equilibrium position. So it's quite nice to say that we can represent both waves on a displacement time graph, and they both look essentially the same shape. Now that has really, really beneficial properties, and we're going to talk about those just now. So, just going grab a piece of paper just to wipe this off. I'm just going to give this a quick spray because that's smooth a little bit. Right, so we're going to talk about some properties of waves now. We've shown how they can be represented, so let's talk more about the visual features of that wave. So I'm going to draw a nice and big one because I'm going to need to do plenty on top of this wave. So I'm going to draw the wave just like that. Now there's a number of features that we have here on this wave which are very, very useful and valuable to any calculations that we might find ourselves doing. So, for example, we've already mentioned the displacement. Now, displacement is quite simply any position that is at a distance from the equilibrium position. So we represent that by the letter x. So we've got lots of displacements here. Any point that is at a distance from the equilibrium point, that's this point here, okay? That's the point between the middle of the oscillations. That's the same for both longitudinal and transverse. Then it has a displacement. A displacement is defined as the distance from an equilibrium point. So there's another word that goes along very strongly with that, and that's the word amplitude. Now, amplitude is really, really important, especially when it comes to talking about sounds, because amplitude, to those of you who are musicians and those of you who are interested in music, will realise that amplitude is all to do with the loudness of a sound. So the louder a sound is, the higher the amplitude will be. So in this case, amplitude is this distance measurement from there to there. It is the equilibrium point to the max displacement, or we can more simply just term this the max displacement from the equilibrium point. So that's the definition of the amplitude. And that is that point there. Obviously, there's two places where you can measure the amplitude. One is where I've already suggested, the other is there. So you can measure the amplitude at those two different positions, just there. Right. The next word for today is one that's a bit more obvious and is of very huge importance, really, and that is wavelength. So wavelength is really easily found. It's not most easily found on this graph. It would be more probably found on a graph where the x-axis was a displacement or a distance between particle oscillations in this case. So generally, wavelength is measured as a point to point from waves. Now unfortunately I can't do it from there because I haven't got a second point that's there, but I can do it from here. So from the start to where it does one full wave is the wavelength. So this, as a distance in meters, is one full wavelength. And it is represented by the symbol lambda. Now that's really important because that symbol is going to come up in an equation later, and so hopefully you will recognise when it does come up, lambda is the wavelength. You can also measure the wavelength in other places because obviously it's the distance between two identical points on a wave. So that's an identical point to that. If you'll notice, if I draw another secondary little wave over here just to give you a bit more to go on, you can see that the wavelength could also be calculated as that distance there, peak to peak. Okay, if I extend the wave onwards, then it could also be calculated from there to there. It's from two identical points, the distance between those two identical points on the wave. They're all the same lambda. That is the wavelength in meters. So that's the wavelength. What we're going to talk about now, however, is the frequency, because frequency goes very strongly hand in hand with the wavelength. Now frequency, if you hear the word frequent, how frequent is something? So if I was talking about students walking in my door, I would say, well, how frequent do students walk in my door? You'd say, well, however many students that walk in per minute or per second or per hour. That is a measure of frequency. Well, in terms of a wave, frequency is how many full wavelengths you get per second. So frequency is an amount of waves or wavelengths, full wavelengths that you get per second. You can also work it out in terms of the time period, because the frequency is how many you get per second. The time period would be 1 over that frequency. So that would also mean that the frequency is equal to 1 over the time period. The time period is the time taken for one full wavelength in seconds. Obviously on this graph you'll see that I've drawn a line very similar position to where I drew the wavelength. That is correct. Wavelength is measured in meters, distance from two identical points, whereas the time period is the time taken to complete a full wave with those particles. And it's measured in seconds, as I've suggested here. So there's a better way of working out the frequency, and there's a way of utilizing an equation that utilizes some of the values and the terms that we've used so far. The equation, the wave equation, is written as V is equal to F lambda. V is the speed of that wave measured in meters per second. So the speed, wave speed. F is obviously the frequency. Lambda, hopefully you've not forgotten by now, it is the wavelength. And that property, that equation is going to be very, very useful for you, and we're going to try utilising that in lessons when you're next in.